Inverse trigonometric functions. Objectives. Understand and use the inverse sine, cosine, and tangent functions. Find the exact value of expressions involving the inverse sine, cosine, and tangent functions. Use a calculator to evaluate inverse trigonometric functions. Use inverse trigonometric functions to solve right triangles. And find exact values of composite functions with inverse trigonometric functions. Understanding and using inverse sine, cosine, and tangent functions. To use inverse trigonometric functions, we need to understand that an inverse trigonometric function undoes what the original trigonometric function does, as is the case with any other function and its inverse. In other words, the domain of the inverse function is the range of the original function and vice versa, as shown in the schematic diagram below. Here we take the measure of an angle, we put it into the trig function, and out comes a ratio. For the inverse trig function, we take the ratio, put it into the inverse trig function, and we get out the measure of an angle. Now, if f of x equals sine x, then we would write f inverse x equals sine inverse x, except we say inverse sine of x. Note that the inverse sine of x is not equal to 1 over sine of x. Now recall that for a one-to-one function, if f of a equals b, then an inverse function would satisfy f inverse of b equals a. Bear in mind that the sine, cosine, and tangent functions are not one-to-one functions. The graph of each of those functions would fail the horizontal line test. Because of this, we need to restrict the domains of each function. We restrict the sine function to a domain of negative pi over 2 to pi over 2. This will help us to include all of the values in the range of that sine function. The cosine function is restricted to a domain of 0 to pi. Again, this is so that we are covering all the possible outputs of the cosine function. The tangent function is restricted to a domain of negative pi over 2 to pi over 2. This takes out all of the other periods of the tangent function so that we only have one of those periods to focus on, and it passes the horizontal line test. And again, it still covers all of the outputs possible in the range. Now, on these restricted domains, we can define the inverse trigonometric functions. The inverse sine function y equals inverse sine of x means x equals sine of y. The inverse sine function is sometimes called the arcsine function and notated arcsine x. We know that the domain and range for functions and their inverses switch, so y equals inverse sine of x has a domain of negative 1 to 1 and a range of negative pi over 2 to pi over 2. The inverse cosine function y equals inverse cosine x means x equals cosine y. The inverse cosine function is sometimes called the arccosine function and notated arccos x. Y equals inverse cosine x has a domain of negative 1 to 1 and a range of 0 to pi, just the same way as the domain and range switch with other inverse functions. The domain and the range for inverse cosine has switched. The inverse tangent function y equals inverse tangent x means x equals tangent y. The inverse tangent function is sometimes called the arctangent function and notated arctan x. Again, y equals inverse tangent of x has its domain and range switched. The domain will be now negative infinity to infinity, and the range will be negative pi over 2 to pi over 2 as an open interval. Graphs of the inverse trig functions for sine, cosine, and tangent. Here we see y equals the inverse sine of x. Again, we could make a quick t-table of the sine function and then switch the x and y entries and regraph it to get the inverse sine x graph. Our domain is going to be from negative 1 to 1, and the range from negative pi over 2 to pi over 2. Similarly, we can find the graph of the inverse cosine x graph. And the domain will be from negative 1 to 1, and the range from 0 to pi. And for y equals inverse tangent of x, we can see how the domain is negative infinity to infinity, and the range is negative pi over 2 to pi over 2, not including the endpoints of that range because we have those as asymptotes. Y equals plus or minus pi over 2. First, let's practice writing these relations as inverse trigonometric functions. Here I have sine of 5 pi over 12 is approximately 0.96593. If we write that as an inverse trigonometric function, we would say the inverse sine 0.96593 is approximately 5 pi over 12. Here, the cosine of 0.5 is about 0.8776. We would write this as the inverse cosine of 0.8776 is approximately 0.5. Note that both of these are in radians. We could do similar work in degrees. Now let's start evaluating these. Evaluate each of the following. Give your answer in radians. Again, similar work can be done with degrees. Here, the inverse sine of 1/2. This is going to mean that the sine of some angle theta is 1/2. So what is the angle that we take a sine of that would give us a half? And remember, we're talking about the inverse sine, and that is pertaining to angles from negative pi over 2 to pi over 2. So the inverse sine of 1/2 is equal to pi over 6. Here, the inverse sine of -1. Remember that this means that the sine of some angle is equal to -1. Again, from negative pi over 2 to pi over 2, where would that occur? That's going to happen at a negative pi over 2. The inverse sine of negative square root 2 over 2. Remember that this means the sine of some angle is equal to negative square root of 2 over 2. Where would this happen between negative pi over 2 to positive pi over 2? That's going to happen at a negative pi over 4. And here, the inverse cosine of negative square root 3 over 2 means that the cosine of some angle was equal to negative square root 3 over 2. Remember, the inverse cosine graph means that the cosine was restricted from 0 to pi. So at what angle between 0 and pi will the cosine of an angle be negative square root 3 over 2? That's going to be at 5 pi over 6. And here we are at inverse tangent of 1. Remember that this means that the tangent of some angle was equal to 1. Remember, the inverse tangent function has to draw from an angle between negative pi over 2 to pi over 2. So at what angle will we have a tangent of 1? That's going to be at pi over 4. The inverse cosine of 1/2. This means that the cosine of some angle was 1/2. Again, between 0 and pi, what angle would give us a cosine of 1/2? That's going to be at pi over 3. Now, there are times when you will need to use a calculator to evaluate inverse trigonometric functions. This is when the angle is not one of our special angles. Just a note, make sure your calculator is in the correct mode before you attempt these problems. Evaluate each of the following. Give your answer in radians. Here we have the inverse sine of 0.97. This means in radians we were given some angle and the sine of it was 0.97. So we're going to go into our trig menu and scroll down to inverse sine. And I know that I have to use the calculator here because 0.97 is not one of our special trig values. So I'm going to put in a 0.97 and I get approximately 1.33 radians. You can choose to write radians, or if you don't write anything at all, the default is that we will understand that's radians. And here, taking the inverse cosine of negative 0.4, again, I know that that is not one of my special angle values, so I'm going to go into the trig menu and scroll down to inverse cosine, and I'll put a negative 0.4 inside, and I get approximately 1.98 radians. Finding the missing measure of a right triangle. Now that we can use inverse trig functions, we are able to find missing angle measures for a right triangle. Let's find the measure in degrees for theta in the given triangles. Here I have an angle theta, and I need to know what that measure is. I am given the adjacent side and the hypotenuse. So we think of what kind of trigonometric function involves the adjacent and hypotenuse. And that's going to be cosine. So I know that the cosine of theta is equal to the adjacent over the hypotenuse. Now I can use my inverse cosine function. If the cosine of theta is 9 over 12, then the inverse cosine of 9 over 12 is going to be my theta. Now, this is not one of our special values, so again, we're going to use the calculator. We want the measure in degrees, so let's make sure that we change our calculator to degree mode if necessary. And we'll go into the trig menu, scroll down to inverse cosine. of 9/12. And here we have a theta of approximately 41.4 degrees. In this triangle, I have my theta, and in relation to that theta, I've been given the opposite side and the hypotenuse. The trigonometric function involving the opposite and the hypotenuse will be sine. So sine of theta is equal to opposite over hypotenuse. Now I know that the inverse sine of 6/10 is equal to theta. Now we're just a few button presses away from finding the angle. I'm still in degree mode. I'm going to go into the trig menu and scroll down to inverse sine, and I'll put in my 6/10, and I get about 36.9 degrees. Remember to put the degree symbol when you're in degrees, otherwise it's understood that you have given a radian measure. Evaluating composite functions with inverse trigonometric functions. Now there are times when we need to compose a trigonometric function with an inverse trigonometric function. In these cases, we can usually find exact values for the resulting expressions without resorting to a calculator. Sometimes we will need to use a calculator. Evaluate the following only using a calculator when necessary. The inverse sine of pi over 3. Now what I know from algebra is that I will work on the innermost set of parentheses first. So the sine of pi over 3 I know is square root 3 over 2. Now the inverse sine of square root 3 over 2, we remember we're pulling angles from negative pi over 2 to positive pi over 2, and the angle is going to be pi over 3. Now, it would almost seem like we just cancel out the inverse sine and the sine, but that's not the case. Let's look at some other problems to show that. Inverse sine of 2 pi over 3. Again, I can work on the inner set of parentheses. The sine of 2 pi over 3 is the square root of 3 over 2. Now I'm taking the inverse sine of square root 3 over 2, just as I did on the last problem. Remember, we're taking values from negative pi over 2 to pi over 2. Those are the angles that we have to choose from. And the angle that satisfies the sine being the square root of 3 over 2 is going to be at pi over 3. Here I have the inverse cosine of the cosine of 2 pi over 3. Again, working on the inner set of parentheses, I know that the cosine of 2 pi over 3 is a negative 1/2. Now it's my job to take the inverse cosine of negative 1/2. Remember, the inverse cosine is going to pull from angles between 0 and pi. So at what angle between 0 and pi is the cosine a negative 1/2? That's going to be at 2 pi over 3. Here, the inverse cosine of the cosine of negative pi over 3. I'm going to work on the inverse cosine being outside, and I can evaluate the cosine of negative pi over 3. That's going to be a positive 1/2. Now, The inverse cosine of positive 1/2 means I'm trying to find an angle between 0 and pi where the cosine is 1/2. And that's going to be the angle of pi over 3. Here, the inverse tangent of the tangent of pi over 8. Now, pi over 8 is not one of our special angles, so this would be a time that's appropriate to use a scientific calculator. So I first make sure that my calculator is in radian mode since the angle given is in radians. And I'm going to take the tangent of pi over 8. So access the trig menu, and the tangent, option 3, of pi divided by 8 is approximately 0.41. So we can replace the tangent of pi over 8 with 0.41. Now keep in mind we're just recording this in 2 decimal places. We're going to try and use the more exact value that's in the calculator so that we don't have round off error in our answer. Now we're taking the inverse tangent of 0.41. So second, trig, we're taking the inverse tangent of the answer we just found, and we'll get about 0.39 radians. Here we have the inverse tangent of the tangent of 11 pi over 9, and again that's not one of our special angles, so we'll go ahead and use the calculator for this one. The first thing that I'll do is evaluate the tangent of 11 pi over 9. So I'm going to go into the trig menu, select tangent, 11 pi over 9, and we'll get approximately 0.84, and then I can take the inverse tangent of that. So go back into the trig menu, enter the inverse tangent, and scroll up to grab that value that we just calculated, and we get approximately 0.70 radians. The inverse sine of the cosine of 13 pi over 6. Now, it might seem like this is not a special angle, but remember, this is coterminal with the angle pi over 6. So there's no need for a calculator here. We can get an exact answer instead of just an approximate one. So this is going to be equal to the inverse sine of the cosine of pi over 6. Now we work on the inside. The inverse sine of the cosine of pi over 6 is square root 3 over 2. Now the inverse sine of square root of 3 over 2, remember we're pulling from angles negative pi over 2 to pi over 2, that's going to be at pi over 3. So we get a nice exact answer on this one. And here I have the inverse cosine of the sine of a negative 11 pi over 4. And again, it seems like this is not one of our special angles, but this is coterminal with 5 pi over 4. So we're going to rewrite this as being equal to the inverse cosine of the sine of 5 pi over 4. Now, the sine of 5 pi over 4 is negative square root 2 over 2. Now, when I'm taking the inverse cosine of negative square root of 2 over 2, we're trying angles between 0 and pi. That's going to be an angle of 3 pi over 4. At times, the Pythagorean identity sine squared theta plus cosine squared theta equals 1, or even right triangle trig, can be used to help us evaluate the composition of these functions. Evaluate the following only using a calculator when necessary. Here I have the sine of the inverse cosine of 4/5. So what I'm wanting to do is find the angle that would give us the cosine of 4/5 and put that here. So let's go ahead and draw a right triangle. We'll call this angle theta. And I know that the cosine is 4/5, that's adjacent over hypotenuse. And from that I also know that this is a 3. I can use the Pythagorean theorem to find that. And so I'm going to replace the inverse cosine of 4/5 with theta. Now the problem is asking, what is the sine of theta? And I know that the sine of theta is the opposite over the hypotenuse. So we end up with a value of 3/5. Here we have the cosine of the inverse tangent of 5/12. So I'm going to take the cosine of the angle that I find when I have the inverse tangent of 5/12. Again, let's go ahead and draw a right triangle. And here is some angle theta. I know for tangent I have the opposite over the adjacent. And in using the Pythagorean theorem, I find the hypotenuse is 13. This is a Pythagorean triple. Okay, again, I don't really necessarily care what that angle is, so I'm just going to replace with this theta. Now, I'm being asked what the cosine of theta is. Cosine is the adjacent over the hypotenuse, so this is the ratio that results. Now the sine of the inverse tangent of 7/4. Here I want the sine of whatever angle it is that gives me a tangent of 7/4. So I'm going to go ahead and draw some angle again. Let's call this angle theta. And I know that the tangent is the opposite over the adjacent. Now, when I put this into the Pythagorean theorem, I know 4 squared plus 7 squared equals c squared. And this ends up being the square root of 65 is my c, my hypotenuse. So whatever the inverse tangent of 7/4 is gives me some angle theta, but the sine of that theta is the opposite over the hypotenuse, 7 over the square root of 65. Most likely you'll need to rationalize the denominator. So we'll have 7 square roots of 65 over 65 as our final answer. We can use a similar process when we need to find a simplified expression for the composition of these functions. Here I need to find a simplified expression for cosine of the inverse sine of x over 3 for x between -3 and 3. Now, I know, based on the process that I had before, I'm just going to say that this is the cosine of some angle theta. And this information here tells me that if this is theta, then the sine of that theta is opposite over hypotenuse. Now I can try and find this missing side. I'll need that because the cosine of theta is the adjacent over the hypotenuse. So let's come to the side and do a little work. We'll say x squared plus a squared equals 3 squared. This means x squared plus a squared equals 9. So a squared is 9 minus x squared, and a is the square root of 9 minus x squared, plus or minus that quantity. Now, I know that the inverse sine has to draw from angles between negative pi over 2 and pi over 2. And the cosine there is always positive in that right half of the plane. So a will end up being the positive square root of 9 minus x squared. Now, the cosine of theta is adjacent over hypotenuse. Now find a simplified expression for sine of inverse tangent for x between negative 1/4 and positive 1/4. Now I'm looking at saying that this is equal to the sine of some angle theta. Let's go ahead and make our right triangle and set this as angle theta. And I know that the tangent of that angle is 4x. That is opposite over adjacent. So 4x over 1. Now I need to find what the hypotenuse is. Using the Pythagorean theorem, 1 squared plus 4x squared equals c squared. I know that 1 plus 16x squared is c squared, and so c is the square root of 1 plus 16x squared. So we can fill that in on the hypotenuse here. Square root of 1 plus 16x squared. And the sine of theta is opposite over hypotenuse. So our simplified expression is 4x over the square root of 1 plus 16x squared. And should I need to rationalize the denominator, I can do that. Multiplying by a form of 1, and I'll get 4x square roots of 1 plus 16x squared all over 1 plus 16x squared.